Okay, welcome all of you again to the tutorial about the spectroscopy. We have been discussing about the rotational spectroscopy, and in the last video we had completed rotational spectroscopy is completed, and in this video onwards we are going to discuss about vibrational spectroscopy or IR spectroscopy. Okay, listen. Vibration spectroscopy, we know that the vibration of molecule, the energy difference or energy levels is in the IR region. So we are using IR radiation in vibrational spectroscopy about 600 to 4000 centimeter inverse. That is, we are using a middle IR region in vibrational spectroscopy. So IR spectroscopy is also known as, vibration spectroscopy is also known as IR spectroscopy because we are using IR radiation, middle IR radiation of ranging from 600 to 4000 centimeter inverse. Okay, and first we are considering vibration of a diatomic molecule, a simple system, a diatomic molecule. We can consider the bond between two atoms as a spring. So even in the very low temperature also the molecule will vibrate, like the vibration of a spring. Okay, so the constant elongation and compression, they need energy, and the energy is depends on the Hooke's law, that is F is proportional to minus K R minus Req. Okay, and energy is equal to half K R minus Req square, and this is the equation of parabola. So the energy diagram will be like a parabola. That is, this is the equilibrium bond distance is this. This is the equilibrium bond distance. This is the lowest energy. When molecule compress or elongate, the energy increases. When compression of elongation increases, the energy also increases. Okay, but even though molecule steps from a particular vibration to higher vibration or a vigorous vibration, the energy increases, but the frequency of vibration remains constant. That is, a molecule or a particular bond has a constant fundamental frequency of vibration. Even though the vibration from a one level to higher level, vibrational vigorousness increases, energy also increases, but vibrational frequency remains constant in the case of a simple harmonic oscillator. This is a simple harmonic oscillator approximation. SHO, simple harmonic oscillator. That is a simple system to begin with. Actually, the vibration is not simple harmonic. So, for the convenience, for the starting purpose, we can consider the oscillation is simple harmonic. Okay, and the energy of the frequency vibration nu is given by the classical mechanics, that is, it is equal to 1 by 2 pi into root of k divided by mu. That is the equation for the frequency vibration, fundamental frequency of vibration. 1 by 2 pi root of k by mu, where nu is the frequency vibration and k is called the force constant, and that depends on the strength of the bond. Higher the strength of the bond, higher will be the force constant. Okay, for weaker bond, k value of k will be less, and mu, as you know, is the reduced mass. Okay, and frequency in terms of wave number, we can write nu bar is equal to 1 by 2 pi c into root of k by mu. Okay, by solving Schrodinger equation for simple harmonic oscillator, we get the energy equation. Energy is equal to, actually it is quantized, energy is equal to V plus half h nu, where V is the vibrational quantum number. Vibrational quantum number, its value is starting from 0, 1, 2, 3, etc. And energy in terms of wave number, we can write epsilon, that is E divided by h nu is equal to V plus half sorry, E divided by Hc, not H nu, E divided by Hc. So H nu divided by Hc, H is cancelled, nu by C is equal to nu bar. So we can write V plus half nu bar, or another term is we are using omega bar oscillation. Omega bar oscillation. So omega bar oscillation is the fundamental frequency vibration in wave numbers. So energy is equal to V plus of H nu, or we can say V plus of H omega. Frequency can be written as in terms of omega or nu, anytime you can use. Or energy in terms of wave number is equal to V plus of omega bar oscillation. Okay, so this will be the energy diagram. For in the case of 0, when V equal to 0, energy is equal to epsilon energy in terms of joule is equal to E0 is equal to V equal to 0, this is equal to half H nu. And epsilon 0 in terms of wave number, it is equal to half omega bar oscillation. Okay, that means even in the 0 state, the energy is not 0. That is, molecule cannot be in the rest. Even at absolute 0, the molecule is vibrating. Okay, and that is the difference between the classical mechanics and in the wave mechanics. From classical mechanics, the energy will be 0 at absolute 0 or at the 0 state. But in quantum mechanics or wave mechanics, energy cannot be 0 in the absolute 0, or energy, there is an energy or a molecule is vibrating even at very low temperature. And that energy at 0 in a state is called 0 point energy. This is the 0 point energy. Okay, so 0 point energy of a simple diatomic harmonic oscillator is not 0, it is equal to half H nu or half omega bar oscillation. And when E is equal to 1, epsilon 1 is equal to, we get 3 by 2 omega bar oscillation. And when E is equal to 2, we get, when V is equal to 2, V is equal to 2, we get epsilon 2 is equal to 5 by 2 omega bar oscillation. Okay, so at lowest level, half omega bar oscillation, then 3 by 2 omega bar oscillation, then 5 by 2, then 7 by 2, like that. That means the difference between the energy level is always is equal to, is a constant, that is 3 by 2 minus 1 by 2 is equal to 1, that is E epsilon 1 minus epsilon 0 is equal to omega bar oscillation, that is 3 by 2 minus 1 by 2 is equal to 1. And E2 epsilon 2 minus epsilon 1 is equal to 5 by 2 minus 3 by 2, that is equal to again 5 by 2 minus 3 by 2 omega bar oscillation, and that is equal to 2 by 2 omega bar oscillation, that is equal to 1 omega bar oscillation. That means the energy difference is always same. That is from 0 to 1 state, 1 to 2, 2 to 3, the energy difference is always same. And this energy difference is equal to omega bar oscillation, or H nu, it is equal to H nu. Okay, so energy levels are evenly spaced. In by simple harmonic oscillator approximation, the energy levels are evenly spaced. The spacing between the energy levels are constant, and we get a constant separation. Okay, that means okay, there is a constant energy separation. Energy of the 0 state V equal to 0 half S nu. Energy of the first state is 3 by 2 omega bar oscillation. Second state 5 by 2 omega bar oscillation. Third state 7 by 2 omega bar oscillation. So difference is always equal to omega bar oscillation. That is a fundamental vibrational frequency. Okay, and the selection rule for harmonic oscillator. The first selection rule is for the radiation to interact, the dipole moment of the vibration should change, or there should be a change in dipole moment during vibration. This is the first important selection rule. Change in dipole moment during vibration. during vibration. That means molecule need not have a permanent dipole moment. Like rotation spectroscopy, in the case of rotation spectroscopy, the molecule should have a permanent dipole moment. In this case, permanent dipole moment is not necessary, but there should be a change in dipole moment during vibration. For example, in the case of carbon dioxide, dipole moment is equal to 0. But vibrations of carbon dioxide, some of them are IR active. Actually, there are 3 vibrations in CO molecule. In the case of CO molecule, there are 3n minus number of vibrations is equal to, as you know, it is for a polyatomic molecule, it is equal to 3n minus 6. Therefore, 3 into 3. For in the case of linear molecule, 3n minus 5. That is equal to 4. 4 vibration. Okay. In that case, this is the first vibration, that is symmetrical stretching. Symmetrical stretching, there would be no change in dipole moment during symmetrical stretching. This is symmetrical stretching vibration. Therefore, it is not IR active. But the other vibration of carbon dioxide, that is unsymmetrical stretching. That is stretching like this. Okay, unsymmetrical stretching. Unsymmetrical stretching. And during this stretching vibration, the dipole moment will change because stretching is unsymmetrical. Therefore, there will be a change in dipole moment. So this vibration will be IR active. And 2 bending modes of vibration. Okay, there are 2 bending modes. In plane bending and out of plane bending, that is also IR active. That is degenerate. Bending modes of carbon dioxide is degenerate. That 2 degenerate bending vibration, that is molecule vibrate bend like this, and in the out of plane vibration will be there, and that 2 vibrations are IR active. So the first condition is change in dipole moment during vibration. So homonuclear diatomic molecule like H2, O2, etc. Okay, they have only one vibration. In the case of H2, there is only vibration, that is symmetrical stretching. So in that case also, there will be no change in dipole moment. So homonuclear diatomic molecule cannot show IR vibration, IR spectroscopy, vibrational spectroscopy, because in that case also there is only one vibration. In the case of diatomic molecule, for homonuclear diatomic molecule, that vibration doesn't bring change in dipole moment. So homonuclear diatomic molecules are IR inactive and rotational inactive. Okay, but carbon dioxide, we know carbon dioxide has no rotational active, rotation is inactive, but they are vibrational active. Some vibrations of carbon dioxide are active. So the condition or the selection rule of IR activity is the change in dipole moment during vibration. Okay, and second selection rule is, okay, next selection rule is for vibrational transition is for simple harmonic oscillator, delta V is equal to plus or minus 1. That is only transition from the next higher level is allowed. All other transitions are forbidden in the case of a simple harmonic oscillator approximation only. Okay. In that case, the difference in energy, that is EV plus 1 minus EV is equal to V plus 1 plus half omega bar oscillation minus V plus half omega bar oscillation, and that is equal to V is cancelled, half is cancelled. Therefore, this is equal to, on solving, we get omega bar oscillation. That means all transition to the next higher level is equal to, that is the frequency nu bar of spectroscopic transition is equal to omega bar oscillation. Okay, and that is also evident from this diagram itself. That is the energy difference between the adjacent energy levels is equal to omega bar oscillation. So all transition to the next higher level will have same frequency. Okay, because energy levels are evenly spaced, energy difference is same. So all transition to the next higher level will be V to V plus 1 or V plus 1 to V transition will have same frequency or same wave number, and that is equal to omega bar oscillation. So it is very interesting that we get only one line in simple harmonic oscillator approximation, and that is equal to the fundamental vibrational frequency of the molecule. That is the spectral frequency of the spectral radiation is also equal to frequency of the fundamental vibration of the molecule. We get only a single line in vibrational spectroscopy. Okay, are you clear? Are you clear? And that is about the simple harmonic oscillator approximation. But actually, the vibration is not simple harmonic. Okay, vibration, there will be anharmonicity. In the smaller vibration, that is up to the levels 5, 6, etc., vibrations are almost simple harmonic. But at the higher vibrational, on vigorous vibration, there is a chance of breaking the bond. Actually, the vibration is not simple harmonic, anharmonicity will be there. So, the potential energy diagram is not the parabola as obtained in the case of a simple harmonic oscillator. This is the case of a simple harmonic oscillator, we get a regular parabola. But in the case of anharmonic oscillator, the diagram look like this blue line, that is, okay, look like this. Okay, so the equation for this type of parabola or this type of figure, potential energy diagram, is given by Morse, and that is called the Morse potential. Morse potential, and that is equal to energy is equal to dEq into 1 minus A e raised to Req minus R. This is e raised to, that is all square, and that's given here. E is equal to dEq 1 minus exponential, there is a here, A is a constant, A into Req minus R, the whole square, where dEq is the dissociation energy. dEq is the dissociation energy. dEq is a dissociation energy, A is a constant. And there is a Morse potential, and that is shown in this blue line. This is the line. This is the actual, I am writing in the red color. This is the actual potential in the case of a anharmonic oscillator case. Okay, and by solving the Schrodinger wave equation, the energy equation will be EV is equal to, as given here, that is EV is equal to, I am writing here, V plus half omega bar E minus V plus half square omega bar E into XE. Okay, clear? That is, for in the case of simple harmonic oscillator, energy EV is equal to V plus of omega bar oscillation, and here it will be V plus of omega bar E, not omega bar oscillation. These are different. Omega bar oscillation and omega bar E are different. That is, technically, term wise they are equal. That is for vibrational frequency of the molecule, but vibrational frequency of a simple harmonic oscillator and an anharmonic oscillator are not same. They are different. Okay, so V plus of omega bar E, that is why it is denoted as omega bar E. In that case, a simple harmonic oscillator case, it was omega bar oscillation. Here it is omega bar E minus another term here, V plus of square omega bar E into XE. Okay, that means with the higher V value, with increase in the V value, the energy decreases. So you can see here, so you can see, as you can see in this diagram, that is, look at this blue diagram, blue energy level. This is the energy difference between V equal to 0 to V equal to 1, and this is V equal to 2. You can see separation decreases, V equal to 3, again decreases, V equal to 4. That green line is for simple harmonic oscillator, that is a constant separation. But in the case of this blue line, that is anharmonic oscillator case, with increasing V value, the separation between the energy levels decreases. Okay, then you can simply understand from this equation, that is EV is equal to V plus half omega bar E minus V plus half square omega bar E into Xc, where omega bar E is the vibrational frequency of the molecule, V is the vibrational quantum number as you know, and Xc is called anharmonicity constant. Anharmonicity constant. Its value is approximately very low value, 0.01, like that. Its value of Xc will be given 0.01 or 0.05 like that. And it is a dimensionless quantity. It is a unitless or dimensionless quantity. Okay. And by rewriting this equation, we can write, here it is omega bar E, we can take this outside. So here there is omega bar E into V plus half, we can take it outside, therefore here remaining is 1, and here omega bar E into V plus half we are taking outside, so here the remaining is V plus half Xc. So we get 1 minus Xc into V plus half, omega bar E and V plus half are outside. Okay, by comparing this with this equation, that is EV is equal to V plus half omega bar oscillation. By comparing with this equation, we get omega bar oscillation is equal to omega bar E into 1 minus Xc plus V plus half. Okay, that's the relation between omega bar oscillation and omega bar E. Okay, that is omega bar E is less than omega bar oscillation, and that increases with the increasing the value of V. Are you clear? That's the relation between omega bar E and omega bar oscillation. Okay, so this I told you, that is omega bar oscillation is equal to omega bar E into 1 minus Xc plus V plus R. That is the relation between omega bar E and omega bar oscillation. And we suppose that if V is equal to, we assume an imaginary level in which V is equal to minus half. That is not possible, but we assume that, suppose an imaginary level, that is V is equal to minus half, then this become 0. In that case, omega bar oscillation is equal to omega bar E. Okay, and in the case of V is equal to minus half, when V is equal to minus half, energy also equal to 0. So omega bar E is actually the fundamental, omega bar E is the equilibrium oscillation frequency of the anharmonic system. It is the equilibrium oscillation frequency of the anharmonic system, the frequency for infinitely small vibration about the equilibrium point. Suppose this is the equilibrium point, there is a very small vibration in that point, energy will be 0, and that equilibrium vibration is called omega bar E. That's a definition that is not that much important, we can leave that. Okay, thus the 0 point energy. What is 0 point energy of the 0 point energy of anharmonic oscillator? Our equation is, what is our equation? E is equal to V plus half omega bar E minus V plus half square omega bar E Xc. When V is equal to 0, this become E0 is equal to half omega bar E minus, here V equal to 0, minus 1 by 4 half square, that 1 by 2 square, that is 1 by 4 omega bar E into Xc. And that is a 0 point energy of the anharmonic oscillator system. This we can also written like this, E0 is equal to, we can write like this, 1 by 4 omega bar E. I am taking this as 1 by 4, so we have to multiply with 2 and 2 here. So here it is 2 minus Xc. Okay, so that is a 0 point energy of the anharmonic oscillator. And selection rule for anharmonic oscillator are found to be delta V is equal to plus or minus 1 and in addition plus or minus 2, plus or minus 3, etc. In the case of simple harmonic system, only plus or minus 1 is possible. But in the case of anharmonic system, plus or minus 1, plus or minus 2, plus or minus 2, plus or minus 3, plus or minus 4, like etc. is possible. But the intensity or probability of transition diminishes. There is a high probability for plus or minus 1 transition and very less probability for plus or minus 2 and even less probability for plus or minus 3. That's the intensity or the probability of transition decreases. Higher probability for plus or minus 1 transition. Okay. And the population of levels also, if you calculate the population of level, you can see that is n v equal to 1 divided by n v equal to 0. That is population of first level divided by population of the 0th level, that is the lowest level, is equal to approximately the we know that our equation of population, that is n1 divided by n0 is equal to e raised to minus delta E divided by kt, and the energy difference between the or we can write like this, e raised to minus, and delta E is equal to, we already know, h nu oscillation divided by kt, and new oscillation is approximately approximately equal to 10 raised to 3, approximately 10 raised to 3. By substituting these values, we get this is equal to e raised to 6.63 into 10 raised to minus 34. This is hc nu bar. We are writing in terms of a number, so it is hc nu bar. So hc is 3 into 10 raised to 10 in centimeter per second velocity of light into nu bar oscillation is equal to 10 raised to 3. By substituting these values and K and temperature 300 Kelvin, we get this is equal to 0.008. That is approximately only 1% is populated in first level. So in room temperature, at room temperature, first level is only negligibly populated. We can calculate that. That is only transition is from V equal to 0 to higher state. That is V equal to 0 to 1. And that is called V equal to 0 to 1 is transition is called fundamental transition. That will be the highest intensity transition, fundamental transition, and V equal to 0 to 2. And that is called overtone transition, and this is first overtone. First overtone. And V equal to 0 to 3 is called second overtone. Or second overtone transition. Okay. The transition from 1 to 2, it is also delta V is equal to plus 1. Okay, it is also possible, but according to the population, we can see that the first level at room temperature is not populated. Only 1%. So we can neglect that transition at room temperature. But this transition is possible. That is, transition from 1 to 2 is possible if you increase temperature. If you increase temperature to 600 Kelvin, this value becomes 0.09. That means in that case 10% population in the first level. So in that case, that is at higher temperature, that is 600 Kelvin, there will be a less intense transition from 1 to 2 transition, and this transition is called a hot band because this transition is possible only at high temperature. The condition for such type of transition, that is from the first level to the second level, take place only at higher temperature because in that case only the first level is populated. So that band is called a hot band. So the main transition is from 0 to 1, delta V equal to plus 1 transition, and that's called a fundamental transition. And there is also less intense transition from 0 to 2, and that's called the first overtone, and from 0 to 3, that's called the second overtone, like that. Okay. And if you calculate the energy for 0 to 1 transition, that is delta V equal to plus 1, we can calculate energy delta E is equal to E V equal to 1 minus E V equal to 0. 0 to 1 transition. So this is 1 plus of omega bar E minus Xc into 1 plus of square omega bar E minus of V equal to 0, that is half omega bar E minus half square omega bar E into Xc. By solving this, we get omega bar E into 1 minus 2 Xc. That is E V equal to 0 to V equal to 1 is equal to omega bar E into 1 minus 2 Xc. And V 0 to V equal to 2, that is first overtone case. The energy is equal to, we are substituting 2 here, so 2 plus of omega bar E, and here also Xc into 2 plus of square omega bar E, minus here 0, that is half omega bar E minus half square omega bar Xc. By solving this, we get 2 omega bar E into 1 minus 3 Xc, that is E V equal to 0 to V equal to 2, that is first overtone. We get 2 omega bar E minus into 1 minus 3 Xc. Okay, similarly in the case of 0 to 3, we get this equation, that is E V equal to 0 to V equal to 3 is equal to 3 omega bar E into 1 minus 4 Xc. So very simple. That is for fundamental transition, that is E 0 to 1 is equal to omega bar E into 1 minus 2 Xc. For first overtone, that is E 0 to 2, it is 2 omega bar E into 1 minus 3 Xc. For second overtone, that is E 0 to 3, is equal to 3 omega bar E into 1 minus 4 Xc. For the third overtone, we can simply write, so there is a pattern here, so we can simply write for 0 to 4, we can write this is 4 omega bar E into 1 minus 5 Xc. Okay, 1 minus 5 Xc. And for another transition, that is 0 to 5, we get 5 omega bar E into 1 minus 6 Xc, like that. And for the hot band, I'm writing here, that is for hot band, that is 1 to 2 transition, E 1 to 2, by substituting V, that is E2 minus E1, that is 2 plus half omega bar E minus 2 plus half square omega bar E minus, by substituting 1 plus half omega bar E minus of minus here become plus, or here we can write all minus 1 plus of square omega bar A Xc. By solving this, we get it is omega bar E into 1 minus 4 Xc. For 0 to 1 transition, we get, for 0 to 1, we get E 0 to 1 is equal to omega bar E into 1 minus 2 Xc. For 1 to 2 transition, that is for hot band, this is equal to omega bar E into 1 minus 4 Xc. Okay. Yes, overtone. And this transition, 3 transition, to a good approximation, when since X is equal to 0, that is E 0 to 1 fundamental band, we get omega bar E into 1 minus 2 Xc. For E 0 to 2 first overtone, we get omega bar E, 2 omega bar E into 1 minus 3 Xc. And E 0 to 3, it is 3 omega bar E into 1 minus 4 Xc. Since Xc is very small, this is actually is equal to, for 0 to 1, if we neglect the bracket term because Xc is very small, we get omega bar E is for fundamental transition, and for first overtone it is 2 omega bar E, and second overtone it is 3 omega bar E. Okay, so it is frequency will be in the multiple case, so that is why it is called an overtone transition. So these spectral signs are very close to omega bar E, 2 omega bar E and 3 omega bar E. The line near omega bar E is called fundamental transition, and while those 2 omega bar E and 3 omega bar is called to first and second overtone respectively. Okay, hot band, I already told you, with increase in temperature, normally the 1 to 2 transition is less probable because the population at the first level is only 1% at room temperature, but when you increase temperature, the there is a probability for 1 to 2 transition, and that's called hot band because it takes place only at high temperature. Okay, this is the equation energy for hot band. I told you omega bar into 1 minus 4xe. Okay, this much I am discussing today in this today's video. Please read the textbook very well, understand the topic very well. Okay, thank you.